Hello, so we'll be discussing about mechanical waves. So for this item, we'll be discussing about periodic waves. The speed of sound in air at 20 degrees Celsius is 344 meters per second. So what is the wavelength of a sound wave with a frequency of 784 Hz corresponding to the note G4 on a piano? And how many milliseconds does each vibration take? And what is the wavelength of a sound wave one octave higher? So that's twice the frequency than the note part in part A. So for A, we can find the wavelength using the formula of wavelength times frequency equals velocity. So we isolate the wavelength. So we'll have the equation now of wavelength equals to velocity over frequency. So it will be 344 meters per second over 784 hertz, and we will be getting 0.439 meters. So now, since we have the frequency, we can now get the period of oscillation. So we'll use the equation of t equals 1 over the frequency, and that's going to be 1 over 784 hertz, and we will be getting 1.28 milliseconds. So for B, if the sound wave is 1 octave higher, which is twice the frequency, the wavelength would be 1568 hertz. That's just times 2 of 784 hertz. So now we can find the wavelength by using the formula of wavelength equals the velocity over frequency. So that's going to be 344 meters per second over 1568 hertz, and we will be getting 0.219 meters. For this item, we will be discussing about the speed of a transverse wave. So one end of a horizontal rope is attached to a prong of an electrically driven tuning fork that vibrates the rope transversely at 120 Hz. The other end passes over a pulley and supports a 1.5 kilogram mass. So the linear mass density of the rope is 0.0480 kilogram per meter. So what is the speed of a transverse wave on the rope, and what is the wavelength? Also, how would your answers to parts A and B change if the mass were increased to 3 kilograms? So for A, we can find the speed of a transverse wave by using the equation of velocity equals the square root of force over the mu. So the force would be the weight, which is mass times the gravitational force. So the linear mass density would be 0.048 kilograms. So it's going to be the square root of 1.5 kilograms times the gravitational force, which is the 9.8 meters per second squared, over the linear mass density, which is 0.048 kilograms per meter. So we'll be obtaining 17.5 meters per second. So now we can find the wavelength. So we can use the equation again, which is the wavelength equals the velocity over the frequency. So it's going to be 17.5 meters per second over 120 hertz, and we will be getting 0.146 meters. Now we can find the speed of a transverse wave using 3 kilograms. So it's going to be velocity equals the square root of the weight over linear mass density. So it's going to be mass times gravitational force over the linear mass density. So that's going to be square root of 3 kilograms times 9.8 meters per second squared over 0.048 kilograms per meter. So we will be obtaining the velocity of 24.7 meters per second. So now we can find the wavelength. So we can use the formula of wavelength equals velocity over frequency. So it's going to be 24.7 meters per second over 120 hertz, and that's going to be 0.206 meters. So for this item, we'll be discussing about energy in wave motion. So a piano wire with mass of 3 grams and length of 80 centimeters is stretched with a tension of 25 newtons. A wave of frequency 120 Hz and amplitude of 1.6 millimeters travels along the wire. So calculate the average power carried by the wire, by the wave, and what happens to the average power if the wave amplitude is halved. So we can find the average power by using the formula of average power equals 1/2 times the square root of linear mass density times force, tangent force, multiplied to omega squared times area squared. So when we input the values here, we would be getting 0.223 watts. So now we can find the average power carried by the wave when the amplitude is half. So you just half the area, and now you will be getting 0.0557 watts. So the average power decreased by a factor of 1/4 when the amplitude is halved.